is Simon. We're going to be chairing this session. And let's just go to this. So we're going to start with the first paper, which is by Henghui Ding, Zhudong Zhang, Bing Shaoi, Ai Qin Li, and Gang Wang. And the title is Context, Contrastive Features, and Gated Multiscale Aggregation for Scene Segmentation.
And if you are the third oral speaker and any of the spotlight speakers, please come up to the front of the podium as soon as possible.
Okay, hello everyone. Welcome to our work, the context contrasted feature and the gated multiscale aggregation for scene segmentation. This is a joint work supported by the Nanyang Technological University, Road Lab, and the Alibaba AI Lab. I'm Henghui, the first author. I'm happy to be here to share with you this work. Okay, first, what is scene segmentation? Scene segmentation aims to classify every pixel in the image. And compared with image classification that assign a label to the whole image, scene segmentation is pixel-level classification. And thus, a well-performed scene segmentation network should classify every pixel well. And in this work, we mainly focused on two challenges of scene segmentation. The first challenge is caused by the various forms of objects or stuff. For example, a pixel may belong to silent or inconspicuous objects, maybe foreground or background. For example, for the first image, the persons are silent part and foreground, where the cars behind them are inconspicuous part and background. And since the scene segmentation needs to classify every pixel, thus, we should pay attention to various forms of objects or stuff. And the second challenge is caused by the existence of multiscale objects. As shown in the second image, the different scale of cars. And in such a case, it is difficult to use a single scale feature to classify all of those pixels. Thus, it is necessary to make use of different scale features. To address those two challenges, we propose two components. The first is context contrasted local model, called the CCR, to address the issue of various forms of objects or stuff, especially for the inconspicuous part that are easily to be ignored. And the second method is gated multiscale aggregation, called the gated sum, to deal with multiscale objects. Okay, next I will present and explain those two methods. First, the context contrasted local features. Please see this image. What we want is to classify the pixel A in this image. The pixel A belongs to the inconspicuous part, the car. And this car are easily to be ignored. If we use a normal convolution, we could collect the local features for this pixel, as shown in the second image. The local features are discriminative and important for this pixel. However, the local features lack of surrounding information, such as the building, road, and other cars, thus are not robust to classify this pixel. And the context is important for scene segmentation. Lots of work devoted to this direction. For example, the dense context showing the third image, and the coarse context showing the fourth image. But both of those contests prefer small representation. Thus, they are easily to be dominated by the silent part. For example, for this image, if we collect the context for pixel A, the context will bring the features of the silent part, the persons. And thus, the context of pixel A will be easily to be dominated by the features of the persons. and the information of the car will be somewhat weakened or even disregarded. So to address this problem, we propose another feature, the context local feature, as shown in the fifth image. The motivation of the context local is that we want to make use of the advantages of both context and local. We want to get the surrounding information, and also we want to protect the discriminative and important local feature. The effect of context local is shown in the last image. As shown in this image, this screen is actually to mimic our human beings. When our human beings look at one object, we will stare at that object. In other words, we pay more attention to that object where we are aware of the surroundings, but the surroundings are somewhat blurred. Okay, next, how can we get the context contrasted local features? Here we use two parallel parts. First, we use a normal convolution to get the local feature, and then we use another dilated convolution to get the surrounding context. After this, we make a contrast between those two. In such a way, we could first make use of the informative context, and also we could protect and spotlight the local features which are discriminative and important. And in our final model, the context contrasted local model, the CCR, several blocks are chained one by one to make multi-level context contrasted local features. And we use such context local feature to do the prediction. And then those predictions are selectively filtered via a gated sum. Okay, let's move to the gated sum. As I talked previously, because the existence of multi-scale objects, it is very necessary to use different scale features. And the skip layers proposed by the FCN is an efficient and effective way to make use of multi-scale features. However, in previous works, the outputs of the skip layers are mainly fused via the sum. The sum fusion could not take into account the individual difference of those inputs, but simply fused all of the features. And thus, the sum fusion could not make a feature selection. To achieve the feature selection, here we propose to add a gate here to control the aggregation of the skip layers and to selectively aggregate the output of the skip layers. So next, let's see how can we get the gates. The motivation of this gated multi-scale aggregation is that we want to adaptively decide the desirable respective fields for every pixel based on its scale and contextual support and so on. So first, to extract such information, we introduce an information skip, the info S here, to extract information from corresponding feature maps and generate information maps. Then, since all of those information maps are get from the same network, thus there will be some sequence relationship among them. For example, from small scale to large scale, from low level to high level. Thus, we input all of those information maps to a recurrent neural network to learn such a sequence relationship. After this, we propose another global refine model to inject the global information to every information map to make sure they are all aware of the global information. And also, in this global refine model, we use a normalization to generate the gates for the gated sum. So up to now, we have already got the gates for the gated sum. Then finally, the outputs of the skip layers are selectively filtered via the gated sum. In such a way, the gated sum could control the information flow of the skip layers and to achieve the feature selection. In a summary, the norm sum is actually a special case of the gated sum where all the gates are fixed to the same value. For example, for this image, if we want to select the features for pixel B. The sum fusion could only simply fuse all of the multi-scale features, but could not select the desirable scale features. And the proposed gated sum, the gates of the desirable scale features will be here, and others are somewhat relatively smaller. In such a way, the gated sum could encourage the preferred scale of features and suppresses others via its gates. And what we need to emphasize is that the value of gates are not fixed after training, but it is generated from a network learned from the training data. Thus, the value of gates vary with the testing image, layers, and the pixel positions. Thus, the gates could make a suitable choice for every pixel's passing. So, here is our overall framework. The proposed context contrast local model, the CCR, is placed on the top of the network to perform high-level contextual modeling and generate multi-level context-aware local features. And the proposed gated sum is used to control the information flow of the network and to selectively aggregate rich scale features from the network. We have done an ablation study here. As shown in the table, the proposed CCR and the gated sum greatly improve the segmentation performance. And also, we can see in this table, the performance gain brought by the gated sum will be here if there are more features for selecting. Here is some qualitative results. As we can see in this image, the proposed network performs better at various forms of objects or stuff. And also, it has a robust adaptability to multi-scale objects. And compared with the state of the art, the proposed network achieves new state of the art on 3 popular Sun segmentation benchmarks: the Pascal contest, Sun RGBD, and Coco stuff. Okay, thank you for the support from the Lab of Nanyang Technological University and the AI Lab of Alibaba Group. Thank you, and welcome to our post for any question and discussion. Thank you.
Thank you. Any questions from the audience? Please come to the mics. Please. All right, I'll ask a question. So you're modeling context, right, which can always also be deceiving. So what happens, or maybe do you have a sense of what happens when you have less frequent classes?
Yes, thank you. A good question. And actually, for this work, we mainly focused on the inconspicuous objects. And thus, to deal with some infrequency classes, we may also field as some other works. But in the future work, to solve such a question, we may give a different weight for the loss to those real classes. Okay, thank you.
Do you have a sense of how the gates look like? Your gates in the network?
Okay. So here we show the gates here. As shown in this image, the gates, the LAN gates, for the LAN gates, if the large scale or regions prefers the high-level features, the large scale features, where the small scale regions prefers the small scale features, and some boundaries also prefers the smaller scale features. Okay, thank you.
Thank you. Let's thank the speaker. Next one up is deep layer aggregation by Fisher Yu, Dechuan Wang, Eval Schellmacher, and Trevor Darrell. And Fisher is going to give the talk.
Hey, everyone. I'm Fisher Yu from UC Berkeley. Today, I'm presenting our work on deep layer aggregation. It's a general network framework that can be generalized into a wide range of image recognition problems. Speaking of image recognition problem, so in the past several years, there has been a lot of work designing various kinds of deep learning models for basically every computer vision problems. And basically, every computer vision problem has a bucket of deep learning models you can choose from. If this slide doesn't really convince you that we have a crazy number of models, I have a second slide to further convince you. So from all this pre-work, we observe two trends. The first thing is, so we are building better and better building blocks for those networks, so that with this network, with those building blocks, we can build a deeper network with a higher accuracy, like what we get from residual blocks or its follow-up works. And also, sometimes we can get more efficient building blocks to improve the overall efficiency of the whole network. And recently, we can even use a small data set to learn the structure for the building blocks and reuse those building blocks on even bigger network and achieve better accuracy. So second trend is people are really like to use skip connection. The main benefit is it's promised that it can fuse the information from like high-level semantics and the low-level spatial resolution. So, and another thing is it can achieve such results with very efficient structure. And recently, we even observed that this trend has been introduced into image classification, which get a very good trade-off between the parameters and the accuracy. However, this kind of network that fuse these two trends together usually require a specific design of building blocks and doesn't really admit our latest design of new building blocks. And therefore, that leads to our first question. So how we can make these two trends more compatible? How we can design the network that can use efficient skip connection and still make it compatible with current building blocks or even future designs? There's actually a second problem with skip connections. So even though that it can give us very efficient structure and promise that it can fuse those semantics and the spatial information very well, so there is still still significant performance gap between the efficient structure and the state-of-the-art model. For example, we can compare the model with skip connection to the just basic dilated residual networks, with stacking all these 3x3 convolution together with dilated convolution, and so that it can achieve high resolution layers without using skip connection. And we can observe that there's still performance gap, and basically on Cityscape, most of the top performing models are using this dilated convolution. That leads to our second question: how we can achieve the accuracy of dilated convolution while we still preserve the efficiency of skip connections? So to solve this problem, we first view the skip connection as a layer aggregation problem. So if we view at the recent work about using skip connection and at a high level, we can see that we can actually use this picture to represent the general idea. So usually we have several subnetworks. Within each network, there is the same spatial resolution or the same number of channels. And there are several such networks to downsample the image. And in the end, we do a top-to-bottom aggregation so that we can upsample the information and fuse the semantic and spatial information. So, and there's one thing we observe here, so for the lowest layer, the aggregation is actually a very shallow network. If there's anything we have learned from past several years, that is, if we want to learn a good representation, we need to use deep network. And therefore, we need to use deep network for layer aggregation. So to realize this idea, let's first look at the image classification problem, which will lead to our hierarchical deep aggregation. So usually the image classification network is a sequentially stacked building blocks. And within each building blocks, it can be different convolution layers. So, and the first thing we do is we look at tree structure aggregation. So with this tree structure, first of all, it can learn to aggregate the information from all layers and create shortcut from all the layers to the output, so that if there's any useful information, it can be passed immediately. And another thing is because the low overhead of this tree structure aggregation, so any block can fit into the bare-bone network, and basically the black box here. And we also observe that we can actually further improve this tree structure aggregation by introducing reentrant aggregation. So the difference here is for each convolution block, instead of taking the output of previous blocks, we can actually take the output of previous subtree so that the input for each convolution block can be more expressive. And based on the idea of deep layer aggregation, we can actually further simplify this network by consolidating the nodes at a high level so that we can have faster aggregation and less overhead. And another thing is, even after this consolidation, the fan-in of each convolution of each aggregation node is still log in terms of the total building blocks we need to aggregate together, so that we can still keep the flexibility of using arbitrary building blocks. So let's look at how we can really use this in an image classification network. So let's first look at, like, say, a ResNet 50, which is very representative for the general image classification network, and it uses this bottleneck building block. So the network is divided into 4 stages, and within each stage, all the building blocks have the same number of channels and the same switch resolution. And to imitate this structure and make fair comparison, so we only change what happens within each stage. And instead of sequentially stacking the building blocks together, we use our hierarchical deep aggregation to connect them together. So when we look at the results, we are very happy to see that just after we switch from the sequential stacking of building blocks to deep layer aggregation, we achieve better trade-off between the accuracy and the parameters. And as a reference, this is the trade-off for DenseNet. And if we use, say, the follow-up building block for ResNext, we can achieve even better accuracy or use better trade-off here. And the same is true for computation. So to further explore this efficiency of this structure, we also shrink the number of channels within each layer so that we can obtain very compact and small models. So here we compare 5 models. All of them have about 1 million parameters. And as you can see that, so our model compared to the other network with similar building blocks can improve accuracy dramatically, and also it can also save computation. So to further verify that this deep layer aggregation can effectively aggregate information from the high-level context to level details, we also test it on fine-grained classification problem. So for example, this is what we get from the airplane classification. So the task is to classify different kind of airplanes. And you can see here, so we apply the DLA network without change on this problem, and it can achieve state-of-the-art performance even compared to the previous model that is specially designed for this problem. And we also test the model on the other data sets that are recent and larger scale, and we find that we can achieve state-of-the-art results on a wide range of them. So that's the image classification. So what about for dense prediction problem, where you need the pixel-wise prediction? So we mentioned that there is a problem of shallow aggregation, and to resolve that problem, we introduced this iterative deep aggregation. Basically, the idea is instead of aggregating from top to bottom, we aggregating from bottom to top. And this figure shows that how we can actually use that to build a real network. So as you can see here, first off, each building blocks here, the number means the downsample ratio of this layer output compared to input images. And as you can see here, each green box here represents iterative deep aggregation. And we are apply this deep aggregation iteratively to get a higher resolution output. And it turns out this structure is working very well on semantic segmentation. Say here we show the results for cityscape semantic segmentation. As you can see here that our model, DLA model, can achieve better performance than the previous network without using dilated convolution, and we achieve a comparable performance with the dilated residual network. And another thing is the benefits of a network is since it doesn't need to preserve the layer resolution at the whole network, we can achieve better memory, we can achieve smaller memory footprint. And let's visualize some results to see what's really happening here. So here is an example image, and you can see that even for the building far away in the background, our network can recover the small detail, like here the antenna from this building. And even for the foreground objects, like say these small shoes, and our network can directly recover the precise boundary of this object. And therefore, we also test our network without change on the boundary prediction problem. And we find that here we try it on BSDS, which has 300 training images. And we find that our network can achieve very good performance and close to human accuracy based on just this 300 images training data. And what's more interesting is when we use this model directly on a larger scale data set like Pascal boundary, we get much better transferability. So basically our performance, we have 10% instead of have like instead of have fraction percent of accuracy improvement, we have like almost 10% improvement. And of course, if we train this model directly on this large data set, we get even better performance. So in conclusion, we propose a new concept, deep layer aggregation for skip connections. And then the deep layer aggregation can achieve state-of-art results on a wide range of problems for image recognition. And if you are interested in the network and how we construct it, you can find the code on our GitHub repo. So just last departing words. So you may be wondering that what if I want to even train this on an even larger data set and on diverse problems? So here is the advertisement. So we recently received the BDD100K data set. So it's a large, diverse video data set, and it comes with a rich annotation. And if you want to label your own data, we also release our labeling platform called Scalable. Make sure you don't spell the domain name wrong. And you can find documentation and the source code on our website. Okay, thanks a lot.
So we've got time for a couple of questions. So any brave souls wanting to ask some questions, please come up to the microphones. We're in both aisles here. And while we're waiting for those brave souls to come up, I've got a question. So you mentioned that the aggregation has benefits in terms of performance and in terms of speed. So, but if you had a focus on one over the other, would you do aggregation differently? Say if we really wanted to kind of like aim for speed, would you do the aggregation in a different manner than if you were aiming for performance?
So I think our aggregation structure is still useful in this case. And what we propose here is how you can connect basic building blocks together. So the first thing, if you want to improve, say, efficiency, probably is you want to design better convolution blocks so that it can be more efficient and it can be more efficiently implemented on the existing hardware. So I think the overall architecture will still apply here.
And then, any other questions? Okay, let's thank the speaker. While we're setting up, I'm noticing that there are 1 or 2 spotlight seats that are still empty. So if you are giving a spotlight, please come up. And we have our next speaker coming up. Yeah, no problem. They'll be giving their talk on convolutional neural networks with alternately updated clique by Yibo Yang, Zixing Zheng, Ting Cheng Shen, and Zhaoshan Lin. And I think we're almost good to go.
Okay, hello everyone. My name is Yang Yibo, currently a second-year graduate student from Peking University. We propose a new convolutional network architecture for image classification tasks and achieve comparable experimental results with state-of-the-art. The CNN architectures have been research focused and have a strong impact on the performance of other tasks in computer vision. In the initial period, a notable trend for those CNN architectures is that the layers are going deeper for better performance. From AlexNet with 7 layers, VGG network with 16 or 19 layers to GoogleNet's 22 layers. However, the gradient vanishing problem prevents from deepening the layers arbitrarily, and the very deep models would make it hard for later layers to access the information from lower level layers. So in highway network, to tackle this problem, a module is introduced to facilitate the information flow from lower layers to high-level layers. And ResNet enables this in a more simple way by skip connections to make deep model very easy to train and make much success. Similarly, ResNet also helps the propagation from low layers to deep layers. It proves that maximizing the information flow by dense connections can further facilitate the training process and get a better performance for image classification. Based on this nets, the question we consider is that how to further improve and maximize the information flow in deep networks. Since dense nets have enabled feed-forward dense connections, we are naturally curious about if feedback connections can be helpful. We know that attention mechanism has been a very hot topic and adopted in many recent literatures. There are different ways to achieve visual attention, such as by formulating an optimization problem, reweighting the activation spatially or channel-wisely, and introducing feedback connections. In a top-down manner, the top-down propagation has been shown to be a very simple way to refine lower-level features and achieve spatial attention, making activations focus on the target region to improve the performance. So both dense connections and feedback connections benefit network training and image classification tasks. If a network can be constructed with both dense connections and bidirectional connections, then it will further maximize information flow and enable feature refinement due to the top-down feedback connections. So based on the motivations, we have a basic block structure proposed. It is named ClickNet. Simply speaking, there are both forward and backward connections between any two layers in the same block. For dense nets, each layer is the output of all preceding layers and the input of all subsequent layers. But for our proposed ClickNet block, any two layers are both the input and output of each other. So there are both forward and backward dense connections in the block. It is more densely connected than dense nets to further improve information flow and at the same time using feedback connections to refine feature maps. During propagation, in the first stage, the layers in a block are initialized using feed-forward dense connections, so it's just like dense nets. But from the second stage, we develop an alternate updating rule based on the intuition that the more lately updated layers correspond to the features with relatively higher level context. So at each update, we use the most lately updated layers to re-update earlier layers. Concretely, from the second stage, except the layer to be updated, all layers are concatenated to, and their corresponding parameters are also concatenated to refine the earliest layer. The propagation process in stage 2 looks like this. The first step, the second step, the third, fourth, and the fifth step. In this way, each layer will always receive the feedback information from the layers that are updated more lately. It achieves a spatial attention mechanism due to the top-down refinement brought by each propagation and makes information communicated sufficiently. We should also note that the parameters in a block keeps reused during propagation. For example, the width W13 in the first stage and the W13 in the second stage are the same parameters. If they are not reused, then this structure is just like deepening the layers, and that's not what we want. So theoretically, our structure can have stage 3 and stage 4 feature without any parameters overhead, but we'll consume training time and maybe GPU memory. So we only consider the first 2 stage features in our work. As for the whole network structure, we adopt a multi-scale way to compose the final representation. We only transit the stage 2 feature into the next block and use another branch to compose the final representation after global pooling. We choose this way because in dense nets, the channels are stacked into later blocks, which causes a progressive increment of computation and GPU memory consumption. We only transit a fixed number of channels into later blocks to prevent parameter and computation's explosion. In experimental section, you will find that despite the fact that ClickNet has bipartite connections in the block, which is double than dense nets, we still have parameter and flops superiorities. we conduct ablation experiments to test the effectiveness of click block. Concretely, we consider 3 cases. For the first case, in ClickNet 1+1, only stage 1 feature is used, which means that the feedback connections are not used at all. For the second case, ClickNet 1+2 uses the stage 1 feature to compose the final representation, but transit the stage 2 feature into the next block. And for the third case, we only use the stage 2 feature. The experimental results show that the stage 2 feature is indeed more discriminative and leads to better performance. From another perspective, we also have the following experiment. In this case, the feedback is not processed entirely. We use the stage 2 feature, but only update the first X steps. If X equals to 0, then it reduces to ClickNet 1+1. If X equals to 5 in this example, then it reduces to ClickNet 2+2. We can find that more alternate updating steps indeed lead to better performance. For our experiments on CIFAR, SVI and ImageNet, we further consider some engineering work to help the performance parameter trade-off. Similar to DenseNets and ResNets, we also add a bottleneck module in our large models to save computation by replacing the 3x3 kernels with 1x1 kernels as the middle layer. And we also adopt the compression module in DenseNets, but we only compress the number of channels before global pooling instead of in the transition layers. In addition, because feedback connections have enabled spatial attention, we also want to incorporate a channel-wise attention mechanism. We add the squeeze and excitation module in each transition layer in order to recalibrate the channels fed into the next block. As for implementation details, we use exactly the same hyperparameters as DenseNets for fair comparison, including the learning rate scheme, batch size, and total training epochs. So this is the experimental results on CIFAR SVI without any data augmentation. K is the number of filters per layer, and T is the total number of layers in all 3 blocks. We can see that when no additional tricks are used, the parameter and computation superiorities of ClickNets are obvious. When K equals to 80 and T is 15, the model has surpassed the best previous performance on 3 data sets with only 1/3 parameters of DenseNet. This is our performance on ImageNet dataset. We also achieve comparable performance with ResNets and DenseNets. Only 1/2 of parameters is needed to be comparable with ResNets. We also provide a discussion to analyze the parameter efficiency and the feature refinement in ClickNets. We visualize the weights in a block with 6 layers in ClickNet and DenseNet respectively. We can see that the most strong weights in DenseNets are distributed along the diagonal, which means that the only neighboring layers have strong dependencies. In this situation, stacking features into deep layers is not a friendly way because long-range, unuseful connections consume much overhead. In ClickNet, the strong weights are distributed more evenly, and the multi-scale method only transits the stage 2 feature into the next block instead of stacking channels. So this helps to explain the parameter efficiency in ClickNets. We also visualize the feature maps in different stages. Here are some examples. We observe that the feature maps in stage 2 diminish the activations of background and the surrounding objects and focus more attention on the target region. This is in line with our motivation that the stage 2 feature after feature refinement should be more discriminative and capable of better performance. Okay, welcome to our poster for more details, and thank you very much.
Questions? At least one question from the audience? All right. So now we've seen a couple of different architectures, how you connect these different layers.
Yes.
Is there something in yours that intuitively can capture better than, let's say, what we saw from Fisher introduced before? Or maybe there's some relationship between these models?
There's a relationship between what?
Between these different models in this section.
In this section?
Yeah. See, you should ask your own question.
The main difference is that our network is designed for a classification task, and many works in this section are designed for semantic segmentation, scene parsing, and such as. But there are relationships to extend our network structure to those tasks.
Okay. And then the slide went fast, but it seems like you had K much larger than T. Is there any motivation or explanation for that?
Yes. Some people notice that in this net, the configuration is larger T and a smaller K, which means that a large number of layers and a small number of filters per layer. And we also we have also tested this configuration, and it has also almost identical performance with our adopted configuration. But we choose our this way because the larger T and the smaller K will cause slightly more GPU memory. So we choose our adopted this way.
Okay, thank you. Let's thank the speaker.
All right, so we have our final oral speaker of the session, and then we'll be transitioning straight to spotlights straight after this. The paper is Practical Blockwise Neural Network Architecture Generation by Zhang, Jiayuan, Wei Wu, Jing Shao, and Chenglin Lu.
Oh, sorry. Hello, everyone. My name is Zhao Zhong. I'm a PhD student at the National Laboratory of Pattern Recognition Institute of Automation of Chinese Academy of Science, a little bit long. I'm also a research intern in SenseTime. This work is done in SenseTime Research Institute. And I will thank to the co-author Jiayuan, Wei Wu, Jing Shao, and Chenglin Liu. I'm so happy to have the opportunity to share my presentation with you today. My topic today is practical blockwise neural network architecture generation. I will talk about why we need continuous design new network architecture and how to construct the network in a smart and automatic manner. So let's get started. Training neural network requires minimizing a high-dimensional non-convex loss function. It's a hard task in theory, but sometimes very easy in practice. In deep learning area, we can often find global minima, only use simple gradient methods. But this trainability of neural network is highly dependent on the network architecture design. It is well known that network architecture with skip connection produce loss function that train easier. And we can see the visualization of the loss surface of ResNet with or without skip connection. So we really need to design the good architecture, but how? Designing a powerful network architecture is a challenging task. But however, there is still no theoretical guidance for designing new network architecture. A high-performance network architecture contains hundreds of possible configurations about the number of the layers, the type of the layer, and so on. It is hence infeasible for manual search, and the design for successful handcraft networks heavily rely on expert knowledge and experience, even a little bit luck or intuition. Except for the network for the image classification, we still need other networks for different tasks. For example, in the human key point task, the state of architecture is not the general network architecture, but the hourglass network. And we also need different networks for different devices like mobile phone. Many works have been proposed, such as ChrisNet, MobileNet, ChevronNet. So the network design is not the end, but just the beginning. We really need a lot of new network architecture, but we actually do not know how to design a network. So how about computer-aided or automatic network design? It's actually not a new research topic. It has been researched for about 13 years. And the early works use genetic algorithm-based optimizer reinforcement learning brute force search to design the network automatically, but these early works cannot get the competitive result compared to the modern handcraft network. So constructing the network in a smart and automatic manner remains an open problem. Some recent work use reinforcement learning to automatically search a good network architecture. Also, they can yield very good performance on small data set like CIFAR. But the huge search space make very heavy computational costs for existing methods. They need hundreds of GPUs to get the human level. Besides, the automatically generated network is limited on a specific data set or task, and that is hard to transfer to other tasks or generalize to another data set with different input size. We can see some famous recent work. This is the early version of Google's NAS. They use 800 GPUs for nearly 1 month and get a very high performance, but the generated architecture is unreadable for human, I think, I guess, and they can only use in CIFAR. And this is Matt Kuhn from MIT. They use less GPUs for 10 days, and they get a very simple plain network, and so the performance is relatively low, and they also can only use in CIFAR. So the two big problems is the heavy computational cost and the generalizability. So we provide a solution to these challenges by a novel fast Q-learning framework called BlockQNN to automatically design the network architecture. It includes these 4 parts: block-wide design, a find optim block with Q-learning, early stop strategy, and distributed synchronous framework. First, to make the network generation efficient and generalizable, we introduce the block-wise network generation. That is, we construct the network architecture as a flexible stack of blocks rather than the whole network. We represent the CNN blocks by a DAG, where each node corresponds to the layer in the CNN, while the directed edge stands for the data flow from one layer to another layer. We also propose a novel layer representation called Network Structure Codes, NSC, as shown in the table. And with this code, we can turn the CNN block into a uniform representation. For example, the ResNet and the inception block can be represented as shown in the table or as shown in the picture. And then we will construct the whole network by stacking this block structure sequentially, which turn a common plane network into its counterpart block vision. The picture shows the two visions of auto-generated network on CIFAR and for imaging that task. So with this block design, we squeeze the search space from entire network to blocks. But there is still a large amount of possible structure to seek. We employ reinforcement learning rather than random sample for automatic design. Our method is based on the stand-up Q-learning. The state represents the status of the current layer, which is defined as the NSC code, and the action is the decision for the next successive layer. And so the learning agent is given the task of sequentially picking the NSC code of a block, and the structure of the block can be considered as an action selection trajectory. And to find the optimal architecture, we asked our agent to maximize its expected reward. For this maximization problem, it is usually used Bell manipulation to optimize it. And empirical assumption to solve the above equation is to formulate it as an iterative update. So the training process can summarize as the agent the agent samples the network structure code according to the Q value, and then stock the blocks to construct the whole network. And we use the network we train the network and get the reward, and at last we use the reward to iterative update the Q value. There's a little trick, and we use reward shaping to speed up the training. It's a very simple trick, but it's very useful in this task. And however, it is still time-consuming to complete the training process to get the reward. To further accelerate the learning process, we introduce an early stop strategy. As we all know, early stopping training process may result in a poor accuracy. It will cause some mistake, which means that some good blocks unfortunately perform worse than the bad block when stop training earlier. Thus, we redefine the reward function. This iteration is inspired from empirical experiments and observations, but it is effective compared to using early stop accuracy directly. And last, we use a distributed asynchronous framework. It consists of 3 parts: master node, controller node, and computer nodes. It can be regarded as a simplified parameter survey, so we can use multi-machine and multi-GPU in this task. This is our result. It just costs us 3 days to complete the searching process with only 32 GPUs, which is superior to the early work spent a month with 800 GPUs to achieve nearly same performance. And as we can see in the picture, the top 2 blocks are found in the final stage of the Q-learning process, which proves the effectiveness of the proposed method. And more important, the block we found on CIFAR can be transferred to ImageNet, and which can also get a competitive result compared to the Minecraft network. Here is some detailed result on CIFAR. We get the state-of-the-art performance, and here is the detailed result on ImageNet. In addition, we do not use more powerful depth-wise convolution operation in the search space, so we can only get a competitive result compared to state-of-the-art model in this vision. And we also compare our methods with the early work. We use less computation resource but get the best performance. Here we do some analysis. This is a block search analysis. We compare the architecture generation effectiveness of our proposed methods with the random search given the equivalent amount of training iteration, and that is the number of sampled networks. And we can see in the picture, after exploitation, our method is obviously better than the random search. And this is the analysis about the evolutional process, and we can find in the process the connection number increase directly, and we can find the shortcut connection and elemental add layers are common in the exploitation stage. So we believe the agent learned that a good block should contain multi-branch architecture, shortcut connection, and even elemental add layers. So there is one more thing. This paper is the work we have done 1 year ago. So let's show some the current progress. And we can the Google released this second vision they called NASNet. This is concurrent with our work, and Google gets the second vision. NASNet is developed for learning cells to construct the whole network with RNN-based controller. They get a really high performance on ImageNet, but we have some problem on how to train the large network, but the performance is already better than all Minecraft network on ImageNet with 2 to 4 input size. So we will keep going on this topic. I'm almost done with my presentation. Thank you very much. Does anyone have any question?
Thank the speaker. We have time for one really quick question, and I think we actually have a question in the corner here.
It's not on. Oh, there it is. Okay. have you tried running it against any regression tasks at all? At the start of the presentation, you mentioned that it might work on regression. Have you tried that yet?
Oh, sorry, I'm not a native speaker. Can you speak slow?
Yeah, I can.
He asked you whether you've performed any regression tests.
Regression test.
So it might be wise to actually kind of take the questions offline for the poster session. And
Okay.
so let's go and thank the speaker. And we might now set up for the spotlight session. So it looks like we have all the spotlight speakers in line, and we're just transitioning now, and we're going to start with our first spotlight speaker. And as we were mentioning too, all the orals and the spotlights have posters too after this session. So there are no questions during the spotlight session, so feel free to come up and harass the authors as much as they like afterwards. And I think we're almost ready to go. We're good? All right.
Hi, my name is Idan Kligosser, and I'm going to present the work XUnit, learning a spatial activation function for efficient image restoration. This is a joint work with Tamar Roth-Shaham and Tomer Michaeli. Deep nets achieve remarkable performance in image restoration. However, state-of-the-art results are typically achieved by extremely deep networks. For example, in super resolution, improvement was achieved mainly by extending the network, reaching tens of millions of parameters. We suggest to weaken the trade-off between performance and efficiency by using a new activation layer called XUnit. The main building blocks of convolutional neural nets are convolutional layers, which are responsible for the spatial processing, and the activation units, which are responsible for the nonlinearity. Typical activation functions are pixel-wise. In this work, we propose to use nonlinear activation units with spatial support. Activation units, like ReLU, can be thought as multiplying the input by a weight map. Unlike ReLU, our unit constructs a weight map where each weight depends on spatial neighborhood of the input. This is done by using depthwise convolution. We also use a nonlinear gating function to map the weights to be between 0 and 1. Merely replacing ReLU with XUnit increases memory consumption. However, XUnit are more suited to image processing tasks and allow to use fewer layers to achieve the same performance. The overall effect is significant reduction in the total number of parameters. In this experiment, we show that the average denoising PSNR is a function of the number of network parameters. The black line is a covenant with the ReLU activation, whereas the red line is the same architecture with ReLU replaced by XUnit. Our architecture can achieve the same performance with only 1/3 of the parameters. An interesting question is how many of the total parameters of the net should we invest in the XUnit activation? While a traditional covenant invests 0% of the parameters, this is suboptimal. We can get a great improvement if we invest 20% of the parameters in the activation. Where is the benefit coming from? Here is a visualization of the feature map at the second layer for two super resolution networks, one with ReLU and the other one with XUnit. With XUnit, more channels participate in the restoration effort. We show that merging XUnit into state-of-the-art image restoration network allows a significant reduction in parameters by using less layers. For example, in denoising, we can reduce the number of parameters in state-of-the-art DNCNN by 1/2 and achieve a better performance. For super resolution, we can do the same with SRCNN or with state-of-the-art SRSNet. Thank you very much.
Hello everyone, I'm Ke Yu. I will introduce our paper. Sorry, I think this is not our paper. Yes, it's not mine. I'm not kidding.
So there's a slight change in the order. We're going to move on to the next one, paper 3, and we're going to come back to paper 2 at the end to get the order right.
Hi, my name is Tamara Chaham, and I'm going to present the work Deformation-aware image compression. This is a joint work with Tomer Michaeli. Lossy compression algorithms aim to compactly encode images while minimizing the restoration error. Popular error measures like the sum of square differences are extremely sensitive to even a slight misalignment. Therefore, to excel under those criteria, the encoder must preserve every fine detail in the exact location of every fine detail in the image. The effect is that when the bit budget is low, like in this example, fine structures are severely brittle. In this work, we present a deformation-aware compression framework, which is based on a new error measure, the deformation-aware SSD. This new error measure is indifferent to slight smooth deformation, thus significantly improving the preservation of fine details in the image. In addition, it can be incorporated into any compression method, including deep net-based ones, while using the encoder as a black box. We show that minimizing the deformation-aware SSD boils down to determining how to best deform the input image so as to make it more compressible. These small deformations are barely noticeable. However, surprisingly, they enable the encoder to preserve delicate features that are otherwise completely lost. Note that this effect is achieved without increasing the bit budget. So how does it work? Lossy compression algorithms solve a rate distortion minimization problem. Namely, during compression, the algorithm selects where to invest bits so as to minimize the distortion between the input image Y and its compressed version X, while conforming a given bit rate. We propose to measure the similarity between X and Y up to some non-rigid deformation T, while penalizing for non-smooth deformations. This is what we call deformation-aware SSD. Pay attention that this distortion measure is in fact an optical flow optimization problem, and therefore may seem difficult to use in rate distortion optimization. However, interestingly, the resulting optimization problem can be solved using a simple alternating minimization. This boils down to iterating between compression and optical flow estimation. Therefore, deformation awareness is completely generic and can be integrated with any compression method while using the encoder as a black box. We tested our approach with a line of compression methods. Let's see some results. Incorporating deformation awareness into JPEG, we managed to restore fine textures that are completely lost using the regular compression. Note again that this effect is achieved without increasing the bit budget. Here's another example with JPEG 2000. Again, we see a similar effect on the roof and the chimney. Our framework can be used with deep net-based methods, like this one of Todorichi et al. Our approach significantly improves the visual quality of this method as well. Deformation awareness is also highly effective with state-of-the-art methods, like WebP. Note how we precisely preserve the words New York. User studies confirm that our framework significantly boosts the visual quality of existing compression schemes. Thank you.
Good afternoon, everyone. My name is Nan. I'm going to present our work on distributed consistent multi-object matching. This is a joint work with Yichen, Bharat, and Leo. So for multi-object matching problem, one of the advantages of it over binary object matching problem is we have a collection of objects, and we could use this collection of data as a regularizer to improve the pairwise object matching quality. That is, we call it cycle consistency. By cycle consistency, what we mean is for every pair of matches, if we verify it using composite matches across other objects within the same collection, we should have the identity map. So one of the big problems having this global kind of regularizer is the scalability problem. Namely, as the data size increases, we're actually facing the problem of this computational bottleneck for this global regularizer. And then the key contribution of our paper is actually we propose a framework that could actually do the distributability and verify the cycle consistency simultaneously. The framework we proposed consists of two stages. The first stage is we actually cluster the collection of objects into overlapping small clusters, as is shown on the image. So we presented an equivalence condition such that under a mild conditions, local consistency across each individual clusters would actually infer the global consistency. And based on this observation, we proposed a greedy algorithm that actually helped to cluster a given collection of objects. And for the second stage, we're waiting for a little bit too long for the second stage, I guess. So for the second stage, is actually after we get this a small cluster of overlapping collections. So what we propose is an iterative message passing algorithm based on ADMM. And the algorithm actually starts from a pairwise matchings, and also starting from the clusters we have from our first stage. And during the iterative update, there are actually 2 steps per iteration. And then the first step is we call inner cluster consistency update. This is the majority of computation happens. And the second step is actually inner cluster message exchange. And that part, we have no computation per se. The only exchange is the information. And that being said, our algorithm, the proposed algorithm is purely distributable. That means every cluster do their computation individually. And thank you. Please visit our poster for more details and the experimentation results.
Hello, everyone. I am Zhang from Northeastern University. Today, I want to talk about the residual dense network for image resolution, which aim to increase the resolution. Here, I mainly focus on deep learning-based method, which can broadly divided into two classes. The first one, extract features in high-resolution space, and the second one in low-resolution space. Both of them have some limitations, and the hierarchical features in low-resolution space are very important. Here, we propose a residual dense block, which includes several convolutional layers, and the dense connections help to use the features from all the layers, and we also propose continuous memory to read state from the preceding block, and the dense features are then fused via local feature fusion. To ease the training, we propose local residual learning. And the output is then divided to the next block. And we further propose residual dense net. Yeah, and extract low-level features and feed into several blocks. And then the features are global feature fusion. And the dense features are upscaled and reconstructed to the high resolution output. Then we investigate the number of blocks and the growth rate and the number of convolution layers to decide parameters. Here we can see large number of block number, convolution layer, and the growth rate contribute to better performance. We use standard training set and benchmark test sets. And we also test on 3 degradation models, BD, DN, and BI. We compare with state-of-the-art methods and follow the same training setting for fair comparisons. Then we conduct application study to demonstrate the effectiveness of our proposed components. We can see that each component makes contribution. The validation PSNR curves for each combination give further demonstrations. And here are some benchmark results with BD and DN degradation models. RDN achieves the best results on both models. And here are results with BID degradation models. Then we will show some visual results. Here the results with BD model are then alleviate blur artifacts. Here are DN model. DN removes noise more deeply. And here are some results with bicubic model. DN recovers much sharper results. And we also present some visual results for scanning factor of 8. Although it's very challenging and difficult, DN recovers much more faithful details and structures. Yeah. And for more details, welcome to our poster. Thank you.
Hello, everyone. I'm Yichen, and I'm an undergraduate student from Peking University. I will present our paper on attentive GAN for range of removal from a single image here. The left image here is the degraded input, and the right image is the result of our method. The problem is intractable, since the first, the regions of range jobs are not given, and the second, the information behind the range jobs is completely lost. To resolve this problem, we apply an attentive generative network using the idea of adversarial training. Our aim is to remove all kinds of range jobs. However, due to the physical formation factor and optical factor while taking a photo, the range jobs shows virus size shapes, colors, and transparency in images. The following tools are examples. And here, we model the range of images by dividing them into the range of layer and the background. The mask is used to describe this division. Here, I introduce our overall network architecture. We inject attention to both the generator and discriminator. I'll discuss the generator first. The generator consists of two parts. The first part is the attentive recurrent network, which will generate an attention map. And the second part is the contextual autoencoder, which takes both the range of image and the attention map as input and produces a corresponding clean background. After that, the discriminator is used to judge whether a given input is real or fake. And here is the detailed architecture of the attentive recurrent network. Its main function is generating an image attention map ranging from 0 to 1. Where the greater the value is, the greater attention will be paid on the pixel. We use a few residue blocks to extract features from the original image, and the convolutional long short-term memory unit is used to do the recurrent estimation. And finally, a few convolution layers is used to form the final attention map. And here is the contextual autoencoder. We apply two kinds of losses here, the multi-scale loss and the perceptual loss. We want to ensure that the generated image is similar to the ground truth in both semantic level and the pixel level. And here comes the discriminative network. We use the label map to guide our discriminator. For generated image, the label map is just the attention map, and for ground truth image, it is replaced by zero matrix, and the final output is a one-dimensional vector, indicate whether it's real or fake. Like many current deep learning methods, we need a dataset to train and evaluate our method. Since there are no current such datasets for range jobs, we made our own with 1,000 image pairs. It consists of various outdoor conditions, background, and range of type, as you can see in the three examples. And here we do some subjective evaluation. The range jobs in the first image is small while densely distributed. We compare with Against method, Photoshop, pixel to pixel, and this is our method. In the second case, the range jobs are large and blurred, and let's check out the performance of the models. And here comes our result. And we visualize our attention map here. We can see that with the increasing of time steps, our method focuses more and more on the range of regions while the noises are eliminated. In all, we have addressed the problem of range of removal from the single image. We have proposed an attentive GAN, and we have collected our own data set. Our method shows impressive experimental results, both qualitatively and quantitatively. For more information, you can come to our post section. Thank you.
Hi, my name is Singh, and I'm from Tencent DO2 Lab. I'm glad to be here to introduce our work on phase super resolution. So basically, phase super resolution aims to recover a high resolution image from a very low resolution input image. And the previous works can be roughly divided into two groups. The first one is image super resolution method, which may not use the feature prior knowledge. And the second one is the phase super resolution methods, which some of them may use the feature priors, but are not trained end-to-end, and the others may be the opposite. So in this work, we want to use the feature priors and end-to-end training simultaneously, and we propose a very deep model that uses online face images for large-scale phase super resolution. So the contributions of this work are: it is the first network that uses facial geometry prior to in an end-to-end training way, and we achieve state-of-the-art performance on online and low-resolution images. And we use alignment and parsing as a novel evaluation matrix to resolve the inconsistency of the classic matrix with the visual perception. So in our network, we first have a core super resolution network for a slightly better output, followed by an encoder to get the features, and the prior estimation network to recover the passing maps and the landmarks, and then they are sent to the decoder. It should be noted that we use ResNet and Hourglass as the backbones for the SR and prior branches. So motivated by the previous works, we also incorporate GAN structure into our framework. We have a reconstruction loss between the recovered images and the target image. We introduce a discriminator and a feature extractor to push the generator for more realistic images. And we then show the effects of the ground truth prior. And in the left, we have a model with ground truth priors, and we also have a baseline that means to remove the prior branch. So the model with ground truth priors are much better. And we also show the model networks with different number of landmarks and different kinds of passing maps, and also a case from the Helen dataset to demonstrate the effects of the ground truth priors. And we then show some comparisons with some state-of-the-art methods. And our proposed FSRNet is much better than the previous works, including the SRSNet. But in this case, FSR again is not good on PSNR and SSIM, but it looks better qualitatively. We then show some comparisons on alignment and parsing as a novel evaluation matrix, and our proposed model is still better than the previous ones. But in this case, FSR gain is even better, which is consistent to the, with respect to the visual perception. So we also show some intermediate phase landmark estimations from the prior branches in different stages. And we also conduct a comparison with some state-of-the-art phase alignment methods, which are estimated directly from the ground truth high resolution images, while ours are estimated from the low resolution input images, which is more difficult. We also show some intermediate passing maps from the prior branches in the second columns, which are competitive to the results of an existing passing approach. So finally, we have released our code, and welcome to poster B22 for more details, and thanks for your attention.
Good afternoon. I'm Ben Mildenhall, and I'm presenting some joint work between Google and UC Berkeley on burst denoising with kernel prediction networks. Modern cell phone cameras can achieve amazing image quality in many situations. However, they still struggle to produce good images in low light situations. Here's an example of a noisy image taken indoors with a cell phone. We could try to reduce noise by taking a longer exposure, but this blurs out the moving people. What if we chop up that long exposure into a burst of short exposures? Now each image will be just as noisy as the original, but the motion will be frozen. Given a burst like this, our task is to denoise the first frame, the reference frame, by incorporating information from all of the frames. We present a learning-based approach for this task. Zooming into the corner of the piano, hardly any detail is visible in the reference, but our network produces a clear output. I'll discuss three key aspects of our burst denoising system. First, our network is able to denoise real burst images after being trained exclusively on synthetic data. Rather than arduously collecting a relatively small real data set, we create a pipeline to generate synthetic data from any internet JPEG dataset, allowing us to quickly generate millions of training examples. We synthesize motion by taking randomly shifted crops from a source image, adjust image histograms to look like linear raw sensor data, and finally add shot and read noise to produce a single training example. Our kernel prediction architecture is inspired by recent work on video interpolation and single image denoising. Rather than calculating pixel values directly, the network produces a set of kernels at each pixel, which are then used to compute a weighted average of the pixel's neighborhood in the burst. In detail, we extract a 5x5 patch around the output pixel from each of the burst images. The network predicts a corresponding kernel for each patch, and the final pixel value is calculated by taking the dot product of the kernels with the patches. One of the most important benefits of using this more complex architecture is interpretability. We can examine the behavior of the network and verify it's doing exactly what we want it to do just by looking at the structure of the output kernels. For example, The kernels applied to the reference frame should always be centered, since the reference frame has no misalignment to be corrected. But the other kernels have two jobs. They have to align and denoise. They should look like shifted deltas or shifted low-pass functions. In frames with extreme misalignment, the kernels should reject the patches by setting their weights to 0. Another way we increase interpretability is with our network's tunable noise level input. During training, we pass in the noise level along with the burst images. The network comes to rely heavily on this noise level channel to determine its denoising strength. When processing a burst at test time, this tunable knob allows us to both decrease denoising strength, with the kernels converging to the identity function on the reference frame, or increase denoising strength, with the kernels drawing more and more heavily on all the frames. Passing the noise level into the network at training time also allows our network to generalize to previously unseen noise levels. Here, we show that a noise-blind network, the green line, performs much more poorly outside the training region. This demonstrates that our network learns to use its noise level input in a meaningful way. We hope these 3 points can prove useful for other researchers working on deep learning for burst and video processing. Thanks for your attention. I'm Ben Mildenhall. Please come see our poster, C3.
Hello, everyone. This is Dr. Ling Chu's work from University of Tennessee, Knoxville. Today, I'm going to help her to introduce her work about hyperspectral image super resolution. A hyperspectral image is essentially a 3D image cube compared to the multispectral image with much less number of bands. The hyperspectral image provides rich spectral information or objects. However, due to the hardware limitations, its spatial resolution is quite low. On the other hand, a multispectral image, although with a low spectral information, they have higher spatial information resolution. In many tasks of computer vision, obtaining high resolution image in both spatial and spectral domain are equally important. So a natural way to generate such image is to fuse a hyperspectral image and multispectral image. So this is referred to as a hyperspectral image super resolution. To fuse images with multimodality, traditional approaches are from mismatch. Most current approaches require a downsampling function as prior, which is not available in real application. This may cause the spectral distortion. To the best of knowledge, there is no deep learning-based approach to solve this kind of problem. We propose the first unsupervised deep learning-based approach named sparse directly net. Assume that the multispectral image and hyperspectral image are linear combinations of spectral and spatial information. So the network consists of two encoder and decoder networks to extract such information. The decoder of the network extracts the spectral information from two images. Since they are taken from the same sense, they share the same decoder. And the representation extracts the spatial information from two images. And since the spatial information has two physical constraints, non-negative and sum to 1, so the representations are designed to follow the Dirichlet distribution to naturally meet these two constraints. Based on the fact that each pixel is a mixture of a small number of spectrals, the representation are encouraged to be sparse using the density function, which increases when the data becomes sparse. Furthermore, in order to encourage the representation to follow the similar patterns, the angle of the representation from two images is minimized. In this way, the sparse distortion will be largely reduced. The quantitative result on two benchmark datasets demonstrates that compared to other methods, the proposed Dirichlet net can preserve spectral information better. This can also be illustrated by visual inspection. For images taken at different wavelengths, the reconstruction error based on the proposed method are always small. And the reconstruction errors are lower than from the state-of-art approaches. Please go to the poster for the details. Thank you for attention.
Hi, my name is Jiayuan, and I'm going to talk about our dynamics in deblurring work. So in this work, we mainly focus on dynamics in deblurring problem. Here is one blur image, and this problem is very challenging as the blur is caused by moving objects, camera shake, and depth variation, and so on. This is one corresponding clear image that we want to recover. To solve this problem, most existing methods assume that the blur kernel is pixelized in locally linear. However, as the motion is complex in real cases, the locally linear assumption does not always hold. Another group of methods use segmentation to solve this problem. They first segment the image into different parts according to the moving objects, and then use the conventional uniform deblurring framework to deblur. However, these algorithms heavily depend on accuracy of segmentation. Recently, the deep learning methods has been employed to solve this problem, which has achieved better results. However, these methods usually use very large deep models which are very computationally very intensive. Now, let me introduce our methods. Our method is motivated by the deconvolution operation. Taking a 1D signal as an example, the blurred image Y can be modeled by this equation, where the K denotes the blur kernel and X is the clear signal. We note that when the size of the blur kernel is 2, the deconvolution operation can be reduced to this one. The detailed derivation can be found in our supplemental material. We note that the equation is in RNN without using nonlinear activation function. Thus, based on this observation, we develop in spatially variant RNN for image deblurring, where the weights are estimated by deep CNN with an encoder and decoder architecture, where the RNN deconvolution is performed in feature space. The network is also trained in an end-to-end fashion. As the spatial variant RNN is our key observation, we also validate its effect. Here are two examples. We can see that without using spatial variant RNN, the proposed method is not able to remove blur. The last two results show that the spatial variant RNN is able to remove blur. So now I will show the experimental results. Here is the quantitative evaluation on the data set by Nan et al. Our method generates high-quality images and is much more efficient. Furthermore, our model is much smaller than the method by them. Here is one image from the dataset. We know that the deblurring results from other deblurring methods still contain significant blur effect. In contrast, our method generates a much more clear image. Now let me conclude our work. In our work, we propose a novel end-to-end spatially variant RNN for dynamics in deblurring. The proposed model is motivated by deconvolution process and has large receptor field yet small model size. In addition, the proposed method achieves state-of-the-art results. Code and dataset are available at our website. Thank you very much for your attention.
Thank you. Hello, everyone, again. just wait for a second. I apologize for that mistake. Hi everyone, I'm Ke Yu. I will introduce our paper, Crafting a Toolchain for Image Restoration by Deep Reinforcement Learning. In this paper, we aim at addressing mixed distortions simultaneously, because in the real world, images may be corrupted by multiple distortions during image capture and storage. In particular, we consider a sequence of Gaussian blur, Gaussian noise, and JPEG compression. We then think of using a single CAN to address mixed distortions. However, such an approach is inefficient and inflexible because all distorted images share the same huge network. Moreover, the restoration process is not transparent. Unlike existing methods, we developed dynamic toolchains that can use tools of different capacities to achieve the desired restoration, and the restoration process is more transparent. Our method is to treat image restoration as a decision-making process. We have an agent use different restoration tools to enhance the image quality. When it observes a noisy image, it decides to try a denoising tool. After one step, the image is still blurry, and the agent decides to try a deblurring tool. And then it observes some artifacts and decides to apply a deblocking tool. Finally, it decides to stop the restoration process as the image quality is good enough. As discussed just now, our framework, namely RL Restore, requires a toolbox and an agent. Next, I'm going to separately introduce these two components. In the toolbox, we designed 12 restoration tools, each of which addresses a simple distortion, including Gaussian blur, Gaussian noise, and JPEG compression. There are two types of lightweight CNN. The 3-layer CNN aims at addressing mild distortions, while the 8-layer CNN aims at restoring severe distortions. We use reinforcement learning to address tool selection. We specify the state, action, and adopts the stepwise PSNR gain as their reward. The agent has a recurrent structure with an LSTM. For more details, please come to our poster. There is another challenge, namely middle state, which refers to the intermediate results after several steps of processing, and none of the tools has seen these intermediate results. To address this challenge, we propose joint training to tune all the tools together. With the tool chain selected by the agent, an image passes forward through the tool chain. Given an MSE loss, the gradients pass backwards along the same tool chain. After a batch of tool chains, all the tools are updated by the cumulative gradients. We test our method on DIV2K dataset. Quantitative results show that our method has competitive performance as a large CNN with more than 80% fewer computations. Qualitative results show that the image quality is enhanced at each step, and our method yields sharper edges with fewer artifacts with a single CNN. We also test our method on real-world images collected by smartphones. Our method generalizes well to real-world scenarios and produces much better results compared to a single CNN. For more information, please search IL Restore and welcome to our poster at B7. Thanks.
All right, so we should probably have another round of applause for the last speaker. He showed a lot of poise with that malfunction, so well done. And yeah, so we'd like to formally kind of close this session. So the next poster session is just outside, food, drinks, fun conversations. Thank you.
I was wondering about your mama. Did she get that job she wanted? So that car that gave her problems.